For as long as we have studied the night sky, black holes have occupied a particular place in our understanding of the universe. They are the endpoints of massive stars, the engines at the centers of galaxies, the places where gravity wins completely. We have imaged one. We have heard the ripples that two of them made when they merged. They are, by almost every measure, as confirmed as anything in modern astrophysics. And yet, there is a problem that has never been fully resolved, a problem that sits at the center of every black hole model we have. Tonight we explore what black holes are, what the observations genuinely confirm, and what some of the most careful minds in physics believe may be sitting in their place. Welcome to Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and reflection. We will begin with the classical picture, the version of black holes that emerged from general relativity and became the foundation of everything that followed. From there, we will move through the observations, the paradoxes, the alternatives, and finally, the open questions that remain. There is no need to hold any of this tightly. It is the kind of subject that rewards a relaxed mind more than an urgent one. Chapter 1. What we thought we knew. The story of black holes does not begin with a telescope. It begins with an equation. In 1915, Albert Einstein published his general theory of relativity, a description of gravity not as a force pulling objects together, but as a curvature in the fabric of space-time itself. Mass, in Einstein's framework, bends the space around it. Other objects then follow the curves that mass creates. The planets orbit the sun, not because the sun is pulling them, but because the sun has shaped the space they move through, and they are following that shape as naturally as water follows a slope. Within months of Einstein publishing his field equations, a German physicist named Karl Schwarzschild found an exact solution to them while serving on the Russian front during the First World War. Schwarzschild's solution described the geometry of space-time around a perfectly spherical, non-rotating mass. It was an elegant piece of mathematics. It was also, in certain respects, a troubling one. The solution contained a boundary. At a specific distance from the center of any sufficiently compressed mass, the mathematics predicted something unusual. Inside that boundary, the curvature of space-time became so extreme that the direction toward the center was no longer just one direction among many. It became the only direction. Everything inside that radius, light included, would be drawn inward with no possibility of return. That boundary is what we now call the event horizon. The radius at which it occurs is called the Schwarzschild radius. For an object with the mass of our Sun, the Schwarzschild radius is roughly 3 kilometers. For the Earth, it is less than a centimeter. Under normal circumstances, neither the Sun nor the Earth comes anywhere close to being compressed to those scales. The event horizon remains a theoretical construct, a boundary that would only appear if the mass was squeezed far beyond anything ordinary physics produces. For several decades after Schwarzschild's paper, most physicists treated the solution as a mathematical curiosity rather than a physical prediction. Einstein himself was skeptical that anything in nature would actually collapse to such densities. The universe, it seemed reasonable to assume, had ways of preventing matter from compressing without limit. Pressure, rotation, quantum effects. Something would intervene before the Schwarzschild radius was ever reached. That assumption began to dissolve in the 1930s. Subrahmanyan Chandrasekhar, a young Indian physicist working in Cambridge, calculated that stars above a certain mass could not be supported by the electron pressure that holds white dwarfs stable. His limit, now called the Chandrasekhar limit, suggested that massive stars had nowhere to go at the end of their lives except inward. Arthur Eddington famously rejected the conclusion, finding it physically absurd. But the mathematics held. Through the 1940s and 50s, the theoretical case for gravitational collapse strengthened. J. Robert Oppenheimer and his collaborators showed that a sufficiently massive star, once its nuclear fuel was exhausted, would collapse continuously. Nothing in known physics would halt the process. The star would pass through its own Schwarzschild radius and disappear behind an event horizon. The term black hole itself did not appear until 1967, when the American physicist John Wheeler used it at a conference and the name stuck. Before that, the objects were referred to by various technical descriptions: collapsed stars, frozen stars, dark stars. Wheeler's term captured something that the others did not. It described not just an object but an absence, a place where light went in and did not come out, a hole in the visible universe. By the 1970s, black holes had moved from theoretical possibility to working assumption. The discovery of quasars, extraordinarily luminous objects at the centers of distant galaxies, suggested that something was powering them from within. The most plausible explanation was a supermassive object consuming surrounding matter at enormous rates. The X-ray binary Cygnus X1, identified in the early 1970s, became the first strong observational candidate for a stellar mass black hole. A compact, invisible object was pulling material from a companion star and heating it to temperatures that produced intense X-ray emissions. The classical picture that emerged from all of this was relatively clean. A black hole forms when a massive star collapses. It is bounded by an event horizon, a surface of no return. At its center is a singularity, a point of infinite density where the equations of general relativity break down. The singularity is hidden from the outside universe by the event horizon. What happens inside remains, in principle, unknowable to any external observer. That picture is the one that has appeared in textbooks, documentaries, and popular science for the past half-century. It is the one most people carry when they think about black holes. And it is, in most respects, an accurate description of what general relativity predicts. The difficulty is that general relativity and the singularity it predicts may not be the final word. Chapter 2. The Singularity Problem. At the center of every black hole, according to general relativity, there is a point where the mathematics stops working. Density becomes infinite. Space-time curvature becomes infinite. The equations that describe gravity, equations that have been tested and confirmed across an enormous range of physical conditions, simply break down. They return values that have no physical meaning. This point is called a singularity, and its presence at the heart of the black hole model is not a minor technical detail. It is a signal that something is missing from the theory. Singularities are not unique to black holes. They appear in other contexts in physics, and in most of those contexts they are treated the same way, as indicators that a model has been pushed beyond its domain of validity. When a calculation returns an infinite value, the usual interpretation is not that infinity is actually present in nature. It is that the theory being used does not apply at the conditions being described. A more complete theory, one that accounts for physical processes the current model ignores, would replace the infinity with something finite and meaningful. In the case of black holes, the missing physics is widely believed to be quantum mechanics. General relativity is a theory of the very large, of space-time geometry, of gravity at cosmic scales. Quantum mechanics is a theory of the very small, of particles, fields, and the probabilistic behavior of matter at subatomic scales. The two theories are extraordinarily successful within their respective domains, but they are fundamentally incompatible with each other in their current forms. No one has yet produced a complete and agreed-upon theory that unifies them. The singularity sits precisely at the intersection of the two. At the center of a collapsing star, matter is compressed to scales so small that quantum effects cannot be ignored. General relativity, applied alone, predicts a singularity. But general relativity applied alone is almost certainly not the right tool for those conditions. The singularity is, in this reading, not a physical object or location. It is a marker, a flag that the theory has reached its edge. Roger Penrose formalized this understanding in 1965 with what are now called the Penrose singularity theorems. Working with Stephen Hawking, he demonstrated mathematically that singularities were not an artifact of simplified assumptions. They were a general feature of general relativity under conditions of sufficient mass and density. If general relativity was correct, singularities were unavoidable. The theorems were a landmark result. They were also, in a quiet way, a confession. General relativity was predicting something that general relativity could not describe. The response to this within the physics community has taken several forms. One approach is to accept the singularity as a real feature of the universe, a place where the known laws of physics genuinely cease to apply, and where asking what is happening is simply not a meaningful question. This view treats the event horizon as nature's way of keeping the singularity hidden, because nothing from inside the event horizon can reach the outside universe. The singularity's pathological behavior is safely quarantined. The outside world is protected from whatever is happening at the center. This is the essence of what Roger Penrose called the cosmic censorship conjecture, the idea that nature always hides its singularities behind horizons, never allowing them to be naked and visible to external observers. Another approach treats the singularity as a clear sign that general relativity must be replaced or supplemented at extreme scales. In this view, the real question is not what happens at the singularity, because a singularity in this sense does not actually exist, but what the correct physics looks like when quantum effects and gravity are properly combined. The singularity dissolves when the right theory is applied. What replaces it is something finite, something physical, something that a complete theory of quantum gravity would describe. This second approach has generated a substantial body of work. Physicists working in loop quantum gravity, string theory, and other frameworks have each proposed ways in which the singularity might be resolved. In loop quantum gravity, the discrete structure of spacetime at the Planck scale, the smallest meaningful unit of length in physics, creates a repulsive effect that halts collapse before a singularity can form. In string theory, the fundamental objects are not point particles, but extended strings, which changes the behavior of matter at extreme densities in ways that may prevent singularities from developing. What these approaches share is the conviction that the singularity is not a destination. It is a question that general relativity cannot answer, and that the physics of the next century may finally be equipped to address. There is a subtler point worth sitting with here. The event horizon and the singularity are often treated as a package, as two features of the same object that must be accepted or rejected together. But they are actually separate predictions arising from different aspects of the theory. The event horizon is a feature of the geometry of spacetime outside the collapsing object. The singularity is a feature of what happens at its center. It is at least conceptually possible to have one without the other. Some of the alternative models we will examine later in this video do exactly that. They preserve something like an event horizon, while replacing the singularity with a physical structure that the equations can actually describe. For now, it is enough to hold the singularity for what it is, not a confirmed feature of the universe, but a gap in our understanding. A place where the best theory we have reaches its limit and gestures, quietly, towards something beyond itself. Chapter 3. The Information Paradox. There is a question in physics that has occupied some of the most careful theoretical minds for more than 50 years. It is not a question about what black holes look like from the outside, or how they form, or how massive they are. It is a question about what happens to the information contained in everything that falls into them. In everyday terms, information means the specific details that distinguish one thing from another. The arrangement of atoms in a book, the precise state of every particle in a cup of water, the quantum properties of every piece of matter that has ever existed. In physics, information has a more precise meaning. It refers to the complete description of a physical system, the full set of data that would allow you, in principle, to reconstruct that system exactly if you had access to all of it. One of the foundational principles of quantum mechanics is that information is conserved. It can be scrambled, redistributed, hidden in complex correlations between particles, but it cannot be destroyed. The total information content of a closed physical system remains constant over time. This principle is so deeply embedded in the structure of quantum theory that violating it would require not just a new discovery, but a fundamental revision of the framework. Black holes appear to violate it. The problem became clear in 1974, when Stephen Hawking made a discovery that changed the way physicists thought about black holes entirely. Working at the intersection of quantum mechanics and general relativity, the same uncomfortable boundary where the singularity problem lives, Hawking showed that black holes are not perfectly black. They emit radiation, not because anything escapes from inside the event horizon, but because of quantum effects at the horizon itself. The mechanism involves the behavior of quantum fields in curved spacetime. Near the event horizon, pairs of virtual particles are constantly being created and annihilated, a feature of quantum field theory that occurs throughout space. In flat, empty space, these pairs appear and disappear without consequence. But near an event horizon, something different can happen. One particle of a pair can fall inside the horizon, while the other escapes to the outside. The escaping particle carries energy away from the black hole. Over time, this process, repeated across the entire surface of the horizon, causes the black hole to lose mass very slowly. It shrinks, and if nothing replenishes it, it eventually evaporates entirely. This radiation is now called Hawking radiation. It was one of the most significant theoretical results of the 20th century. It was also the source of a profound difficulty. The problem is that Hawking radiation, as Hawking originally calculated it, is thermal. It carries energy away from the black hole, but it carries no information about what fell in. It is the same regardless of whether the black hole formed from a collapsing star, a collection of books, or a vast cloud of hydrogen gas. The radiation is essentially random, described entirely by the black hole's mass, charge, and rotation, and nothing else. When the black hole finishes evaporating, everything that ever fell into it, all the information about the specific physical states of all that matter, appears to be gone. This is the information paradox. If Hawking's calculation is correct, black holes destroy information. But if quantum mechanics is correct, information cannot be destroyed. Both of these statements cannot be simultaneously true. Hawking himself initially argued that the information was genuinely lost, that black hole evaporation represented a real breakdown of quantum mechanics, a place where the usual rules did not apply. Most physicists found this deeply uncomfortable. Losing information meant losing the ability to predict the future from the past, at least in principle. It meant the universe was fundamentally less ordered than quantum mechanics required. The decades that followed produced a sustained effort to resolve the paradox without abandoning either general relativity or quantum mechanics. One influential proposal came from the framework of string theory and the principle of black hole complementarity, developed in the 1990s by Leonard Susskind and Gerard 't Hooft, among others. Their argument was that information is not lost. It is encoded in the Hawking radiation in a highly scrambled form, spread across subtle quantum correlations between the emitted particles. An observer outside the black hole, given infinite time and computational resources, could in principle reconstruct everything that had fallen in by carefully analyzing the radiation. The information would be preserved, just extraordinarily difficult to recover. This view gained significant support when Juan Maldacena demonstrated in 1997 that certain gravitational systems are mathematically equivalent to quantum field theories without gravity. This correspondence, known as the ADS/CFT correspondence, strongly suggested that black hole evaporation must be consistent with quantum mechanics, because the equivalent quantum field theory manifestly preserved information. It did not explain the mechanism by which information escaped, but it made the loss of information seem increasingly implausible. The debate took a sharp turn in 2012 when a group of physicists including Ahmed Almheri, Donald Marov, Joseph Polchinski, and James Sully published a paper that became known in the physics community by the acronym AMPS, after their initials. Their argument was startling. They showed that the three assumptions most physicists had been working with, that information is preserved, that an observer falling into a black hole experiences nothing unusual at the event horizon, and that quantum field theory works normally far from the singularity, could not all be simultaneously true. At least one of them had to be abandoned. If information escapes in the Hawking radiation, the radiation cannot be in the smooth, calm quantum state that general relativity predicts at the horizon. Instead, the horizon would have to be a place of violent quantum activity, a wall of high-energy radiation that would incinerate anything falling through it. This became known as the firewall. The name is apt. An infalling observer, rather than crossing the event horizon smoothly and noticing nothing unusual, would be destroyed at the boundary. The firewall argument remains unresolved. Different physicists have responded to it in different ways. Some accept the firewall and conclude that the event horizon is a more dramatic place than general relativity suggests. Some argue that the firewall argument contains subtle errors and that a correct treatment of quantum gravity would dissolve it. Some take the paradox as evidence that the event horizon itself, as classically defined, may not exist in the form general relativity predicts. That last response is particularly significant for the larger question this video is exploring. If preserving information requires modifying what happens at the event horizon, then the event horizon as we understand it may need to be replaced. And if the event horizon changes, then what we call a black hole changes with it. Chapter 4. What the observations actually show. It is worth pausing here before moving further into the theoretical landscape to consider what we have actually seen. The paradoxes and alternatives discussed in this video are not the product of idle speculation. They arise from serious attempts to reconcile the black hole model with the rest of physics, but they exist alongside a body of observational evidence that is, in its own right, remarkable. Understanding what that evidence actually confirms and what it leaves open is essential to holding the full picture clearly. The first indirect evidence for black holes came not from imaging, but from the behavior of matter around them. In the early 1970s, astronomers identified Cygnus X1, a powerful source of X-ray emission in the constellation Cygnus. The X-rays were coming from superheated gas being pulled from a visible companion star toward an invisible compact object. The mass of that object, inferred from the orbital dynamics of the companion star, was too large to be a neutron star. The most natural explanation was a black hole. Cygnus X1 became the first widely accepted stellar mass black hole candidate, and the method used to identify it, measuring the gravitational influence of an invisible object on its visible companion, became a standard tool of observational astronomy. Over the following decades, dozens of similar systems were identified. Each one presented the same basic picture: a compact, invisible object of sufficient mass pulling material from a companion and heating it to temperatures that produced characteristic X-ray signatures. The cumulative weight of these observations built a strong circumstantial case for the existence of objects consistent with the black hole model. The case for supermassive black holes at the centers of galaxies developed along a parallel track. By the 1990s, astronomers were using infrared telescopes to track the orbits of individual stars near the center of our own galaxy. The stars were moving in ways that required an enormous concentration of mass at a single point, a mass equivalent to roughly 4 million suns, contained within a region smaller than our solar system. The object at the center of the Milky Way, now known as Sagittarius A star, became the strongest candidate for a supermassive black hole in the local universe. The precision of the stellar orbit measurements, carried out over more than 2 decades by teams led by Reinhard Genzel and Andrea Ghez, work that earned them a share of the Nobel Prize in Physics in 2020, left little room for alternative explanations within conventional astrophysics. Then, in 2015, came an observation of a different kind entirely. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected gravitational waves for the first time. The signal, designated GW 1514, was produced by the merger of 2 black holes roughly 1.3 billion light-years away. The 2 objects, with masses of approximately 29 and 36 times the mass of the Sun, spiraled toward each other over billions of years and merged in a fraction of a second, releasing an amount of energy equivalent to roughly 3 solar masses entirely in the form of gravitational waves. The signal lasted less than a second in the detectors. Its shape matched, with extraordinary precision, the predictions of general relativity for exactly this kind of merger. LIGO and its partner observatory Virgo have since detected dozens of additional gravitational wave events, mergers of black holes with other black holes, and mergers of neutron stars with each other and with black holes. Each detection has been consistent with the predictions of general relativity. The gravitational wave signals carry information about the masses, spins, and distances of the merging objects, and in each case, the data fits the black hole model cleanly. The most visually striking piece of evidence came in 2019, when the Event Horizon Telescope collaboration released the first direct image of a black hole shadow. The target was the supermassive black hole at the center of the galaxy Messier 87, roughly 55 million light-years away. The image showed a bright ring of glowing gas surrounding a dark central region, the shadow cast by the event horizon against the glowing material behind it. The size and shape of the shadow matched the predictions of general relativity for a black hole of approximately 6.5 billion solar masses. In 2022, the same collaboration released an image of Sagittarius A star at the center of our own galaxy, confirming the presence of a similar shadow structure much closer to home. These observations are genuinely extraordinary. They represent some of the most precise confirmations of general relativity ever achieved, and they are entirely consistent with the black hole model as described by that theory. But it is important to be precise about what they confirm. The gravitational wave signals confirm that two massive compact objects merged, and that the merger proceeded as general relativity predicts. They do not directly probe what is happening at or inside the event horizon. The event horizon telescope images show a shadow, a region where light is being bent and captured by an extremely compact massive object. They confirm the presence of something that bends light in the way a black hole would. They do not show the event horizon itself, which by definition cannot be seen directly. They do not show the interior. They do not confirm or deny the existence of a singularity. This distinction is not a criticism of the observations. It is simply an honest accounting of what any observation from the outside of an event horizon can tell us. The event horizon, if it exists as general relativity describes, is a one-way boundary. Information from inside it cannot reach us. No telescope, however sensitive, can see through it. Everything we observe comes from outside, from the behavior of matter and light in the strong gravitational field surrounding the object, not from the object's interior. What the observations confirm, with high precision, is that extremely massive, extremely compact objects exist, and that their influence on surrounding matter and space-time matches the predictions of general relativity very closely. That is a substantial confirmation. It is not, however, a confirmation that a singularity exists at the center, that the event horizon is precisely as general relativity describes, or that the interior of these objects contains nothing other than what the classical model predicts. The objects we are observing are consistent with black holes. They may also be consistent with something else, something that produces the same external gravitational signature while differing in its internal structure. That possibility is not ruled out by any observation currently available to us. It is, in fact, the central question that the theoretical alternatives we are about to explore are designed to address. Chapter 5. The Case Against Singularities. The singularity at the center of a black hole is not a feature that physicists have quietly accepted and moved past. It has remained for decades a source of genuine unease in theoretical physics, not because it is unfamiliar, but because it is understood too well. A singularity in a physical theory is not a discovery. It is a diagnosis. It tells you that the theory being applied has reached the boundary of its own validity, and that something beyond it is needed to describe what is actually happening. This view is not a minority position. It is shared by a broad range of physicists working across different theoretical frameworks. The disagreements are not about whether the singularity is a problem. Most agree that it is, but about what replaces it, and what the replacement implies for the structure of the black hole as a whole. The argument against physical singularities rests on several foundations. The first is historical precedent. Physics has encountered apparent singularities before, and in each case, the the singularity has turned out to be an artifact of an incomplete model rather than a genuine feature of nature. The ultraviolet catastrophe of classical electromagnetism, the prediction that a perfect black body would radiate infinite energy at short wavelengths, was resolved by quantum mechanics, which introduced a natural limit to how energy is exchanged between matter and radiation. The singularity did not survive contact with a more complete theory. There is strong reason to expect the same outcome for the singularities in general relativity. The second foundation is dimensional. The singularity in a black hole is predicted to exist at scales far below anything general relativity was designed to describe. The Planck length, roughly 1.6 times 10 to the power of negative 35 meters, is the scale at which quantum gravitational effects are expected to become dominant. It is derived from three fundamental constants: the speed of light, the gravitational constant, and Planck's constant. Below this scale, the smooth, continuous space-time of general relativity is almost certainly not the right description of reality. Whatever space-time actually is at those scales, whether discrete, foamy, or structured in some other way entirely, the classical prediction of a point of infinite density is almost certainly not it. The third foundation is consistency, a physical singularity, a place where density is genuinely infinite and the laws of physics break down, would represent a fundamental rupture in the fabric of the universe. It would be a location where cause and effect cease to operate, where predictability ends, where the entire framework of physics becomes inapplicable. Most physicists find it more plausible that the laws of physics continue to hold everywhere, and that the singularity is a sign of theoretical incompleteness rather than a genuine feature of nature. Roger Penrose, whose singularity theorems did more than almost anyone else's work to establish that singularities were unavoidable within general relativity, has spent much of his subsequent career thinking about what this means. His cosmic censorship conjecture, the proposal that nature always hides singularities behind event horizons, was partly motivated by the desire to preserve the predictability of physics for external observers. But the conjecture does not resolve the singularity itself. It merely quarantines it. The problem remains inside the horizon, even if its consequences cannot propagate outward. Other physicists have taken the position that censorship is not enough. If the singularity is unphysical, if it represents a failure of the theory rather than a real location, then the correct response is not to hide it, but to replace it. This is the motivation behind a range of theoretical proposals that begin not with the question of what black holes are, but with the question of what they cannot be. One influential line of argument focuses on the formation process itself. A black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. The collapse proceeds inward, and in the classical general relativistic picture, nothing halts it. But this picture assumes that general relativity remains valid throughout the collapse, all the way down to arbitrarily small scales. If quantum effects become significant before the Planck scale is reached, and there are theoretical reasons to think they might, then the collapse may not proceed to a singularity at all. Instead, it may be halted by a quantum pressure, a repulsive effect arising from the discrete structure of space-time, or from quantum field interactions that general relativity does not account for. This halting mechanism has been explored in detail within loop quantum gravity. In that framework, space-time is not a smooth continuum, but is composed of discrete units at the Planck scale, a kind of quantum granularity that becomes significant only at extreme densities. When a collapsing star reaches Planck density, the discrete structure of space-time generates a repulsive force strong enough to halt and reverse the collapse. The result is not a singularity, but a bounce, a moment at which the inward collapse reaches its minimum volume and begins to expand again. What this expansion looks like from the outside, and whether it is observable, depends on the specifics of the model. But the singularity itself is replaced by a finite physical event. String theory approaches the same problem from a different direction. In string theory, the fundamental constituents of matter are not point particles, but one-dimensional extended objects, strings, whose finite size sets a natural minimum length scale. Point-like singularities, which arise from treating particles as mathematical points with no spatial extent, cannot form in a universe where the fundamental objects always occupy a finite region of space. The strings spread out the matter that would otherwise collapse to a point, replacing the singularity with a structure that the theory can describe without breakdown. What these approaches have in common is the conviction that something physical occupies the region where the singularity is predicted, not an infinity, not a breakdown, a finite object with describable properties governed by laws that remain consistent and predictive. The nature of that object, what it is made of, how it behaves, what it looks like from outside, varies between frameworks, but the conclusion is shared. The center of a black hole is not empty of physics. It is full of physics that general relativity alone cannot see. This conclusion has consequences that extend beyond the center. If something physical occupies the interior, then the interior has structure. And if the interior has structure, then the event horizon, the boundary between the interior and the exterior, may not be exactly what general relativity predicts either. The horizon, in the classical model, is defined by the singularity it surrounds. Change what is at the center, and you may change what the boundary looks like as well. That connection between interior and boundary is one of the most active areas of current theoretical research. It is also one of the reasons why the alternatives to the standard black hole model are not merely academic exercises. They have implications for what we might one day be able to observe, and for what the objects we are already observing actually are. Chapter 6. Gravastars. In 2001, two physicists named Pavel Mazer and Emil Motola proposed an alternative to the black hole that was unusual in a specific way. It did not simply modify the interior of a black hole or smooth out the singularity. It replaced the black hole with a fundamentally different kind of object, one that had no singularity, no event horizon in the classical sense, and no interior region from which nothing could escape. They called it a gravitational vacuum condensate star. The name was quickly shortened to Gravastar, and it has remained one of the most carefully studied alternatives to the black hole model in the 2 decades since. The Gravastar begins with a question that Mazer and Motola considered underexplored. What if the collapse of a massive star does not produce a region of trapped spacetime, but instead triggers a phase transition, a change in the fundamental state of matter and spacetime in the collapsing region, analogous to the phase transitions that occur when water freezes or a material becomes superconducting. Phase transitions in ordinary matter are driven by changes in temperature and pressure. At the extreme densities reached during gravitational collapse, the conditions are unlike anything in ordinary experience, and Mazer and Motola argued that the vacuum of spacetime itself might undergo a transition under those conditions. In their model, the interior of a gravastar is filled not with collapsing matter or a singularity, but with dark energy, a form of energy associated with a repulsive pressure that pushes outward rather than pulling inward. This interior is separated from the exterior by a thin shell of ultra-compact matter in an exotic quantum state. Outside that shell, the space-time geometry is identical to that of a black hole of the same mass. An observer far from the object would see the same gravitational field, the same light bending, the same orbital dynamics as they would around a black hole. The external signatures are, for practical purposes, indistinguishable. The key difference is at the surface. A gravastar has no event horizon in the absolute sense. Where a black hole has a boundary beyond which nothing returns, a gravastar has a physical surface, extremely compact and extremely difficult to interact with, but a surface nonetheless. Matter falling toward a gravastar does not cross an event horizon and disappear into an interior from which it cannot escape. It approaches a physical boundary and interacts with it. The information carried by that matter is not lost. It remains encoded in the state of the surface and the radiation it eventually produces. This resolution of the information paradox is one of the gravastar's most appealing theoretical properties. Because there is no event horizon in the strict sense, there is no interior from which information cannot escape, and no need to invoke firewalls or exotic modifications of quantum mechanics to account for the fate of infalling information. The information is preserved at the surface in the same way that information is preserved when matter interacts with any other physical object. The dark energy interior also addresses the singularity problem directly. The repulsive pressure of dark energy provides exactly the outward force needed to halt the collapse before a singularity forms. The infalling matter never reaches a point of infinite density because the dark energy pressure increases as the interior is compressed, eventually balancing the gravitational force and stabilizing the object at a finite size. The interior is in a state of very high but finite density, governed by equations that remain physically meaningful throughout. From the outside, a gravastar is extraordinarily difficult to distinguish from a black hole. Its mass, its gravitational influence on surrounding matter, and its effect on the paths of light are all essentially identical to those of a black hole of the same mass. The Event Horizon Telescope images, the gravitational wave signals detected by LIGO, and the stellar orbit measurements around Sagittarius A star are all consistent with a gravastar as well as with a classical black hole. Current observational technology cannot resolve the difference. There are, however, subtle signatures that future observations might be able to detect. The most promising involves what happens when matter falls onto the surface of a gravastar, rather than disappearing behind an event horizon. When matter strikes a physical surface, it releases energy, the kinetic energy of infall converted to heat and radiation. This emission would be absent in the case of a true black hole with an event horizon, because infalling matter simply crosses the horizon and contributes to the interior without any surface interaction. If future telescopes with sufficient resolution could detect the characteristic radiation from such surface interactions, it would distinguish a gravastar from a black hole in principle. Gravitational wave observations offer another potential avenue. When two compact objects merge, the details of the merger and the ring down, the way the merged object settles into its final state by emitting gravitational waves, depend on the internal structure of the objects involved. The ring down of a gravastar merger would differ subtly from that of a black hole merger, because the gravastar has a physical surface that responds to the merger dynamics differently from an event horizon. As gravitational wave detectors become more sensitive and accumulate more merger events, the statistical properties of the ring-down signals may begin to reveal whether the merging objects have surfaces or horizons. the Gravastar remains a theoretical proposal. It has not been confirmed observationally, and there are open questions about its formation mechanism and long-term stability. Some analyses have suggested that the thin shell of exotic matter at its surface would be unstable under perturbation, that small disturbances would cause it to collapse or expand, rather than remain in equilibrium. Maser, Motola, and others have argued in response that a fully quantum mechanical treatment of the shell resolves these stability concerns, but the question has not been definitively settled. What the Gravastar represents, regardless of whether it turns out to be the correct description of nature, is a serious and mathematically coherent alternative to the black hole. It demonstrates that the external signatures we associate with black holes do not uniquely require the internal structure that the classical model predicts. The same gravitational field, the same light bending, the same compact mass. All of these can be produced by an object that has no singularity, no event horizon, and no information paradox. The Gravastar does not prove that black holes do not exist. It proves that the question of what these objects are on the inside is genuinely open. Chapter 7. Fuzzballs. If the Gravastar emerges from thinking about phase transitions and dark energy, the fuzzball emerges from a completely different direction. It is a product of string theory, the framework that attempts to describe all fundamental particles and forces in terms of tiny, vibrating, one-dimensional objects called strings. String theory has been one of the most ambitious and most contested theoretical programs in physics for the past several decades. It has not yet made predictions that can be tested with current experimental technology, and its status as a physical theory rather than a mathematical framework is a matter of ongoing debate. But within its own terms, it has produced a remarkably detailed and internally consistent alternative to the black hole, one that resolves both the singularity problem and the information paradox in a single stroke. The fuzzball was developed primarily through the work of Samir Mather and his collaborators, beginning in the early 2000s. Mather's starting point was the information paradox. He took seriously the conclusion that information could not be lost, and asked what a black hole would have to look like from the perspective of string theory in order to preserve it. The answer he arrived at was striking. A black hole, in string theory, is not a region of empty curved space-time surrounding a singularity. It is a dense, tangled ball of strings and higher dimensional objects called brains, a fuzzball, whose size is comparable to the event horizon of the equivalent classical black hole. In the classical model, the event horizon is a geometric boundary in otherwise empty space-time. Nothing physically exists at the horizon itself. It is defined purely by the curvature of space-time, by the fact that from that radius inward, the future always points toward the center. A fuzzball replaces this empty geometric boundary with a physical surface. The strings and brains that make up the fuzzball extend all the way out to the scale of the would-be horizon. There is no empty interior. There is no singularity. The entire volume that the classical model describes as the black hole's interior is instead filled with the complex quantum mechanical structure of the string configuration. This has an immediate consequence for the information paradox. In the classical black hole, information is lost because it falls through the event horizon into an interior from which nothing can return, and the Hawking radiation that eventually carries energy away is thermal. It carries no information about what fell in. In the fuzzball picture, there is no empty interior and no event horizon in the classical sense. Matter falling toward a fuzzball does not cross a featureless geometric boundary. It interacts with the physical surface of the string configuration. The radiation emitted by a fuzzball is not thermal in the way Hawking's original calculation suggested. It carries information about the state of the strings, and therefore about everything that has ever interacted with the fuzzball's surface. Information is preserved, not because of some exotic modification of quantum mechanics, but because the object itself is a quantum mechanical structure all the way to its surface. The fuzzball also resolves the singularity naturally. There is no point of infinite density at the center, because there is no empty interior in which a singularity could form. The strings and branes fill the space. Their quantum mechanical behavior sets a natural minimum scale, the string length, below which the classical notion of a point in space loses meaning. The collapse that general relativity predicts to produce a singularity is, in the string theory picture, halted by the physical extent of the fundamental objects. The matter does not collapse to a point. It settles into a complex quantum state, a specific configuration of strings and branes, whose total size is set by the energy and quantum numbers of the system. One of the most remarkable features of the fuzzball proposal is that it is not just a qualitative picture. For certain highly symmetric black holes, technically called extremal charge black holes, Mather and his collaborators were able to count, using string theory methods, the precise number of distinct fuzzball configurations that correspond to a black hole of a given mass and charge. The logarithm of that number, a measure of the entropy of the system, matched exactly the Bekenstein-Hawking entropy formula, which had been derived decades earlier from purely thermodynamic arguments applied to the classical black hole. The agreement was exact, not approximate. This matching is considered one of the most significant results in theoretical physics of the past 30 years, because it provided a microscopic, statistical, mechanical explanation for a thermodynamic property of black holes that had previously lacked any such foundation. The Bekenstein-Hawking formula states that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This is deeply counterintuitive. In ordinary thermodynamics, the entropy of a system, a measure of the number of microscopic states consistent with its macroscopic properties, scales with its volume. A larger box contains more possible arrangements of its contents. A black hole's entropy scaling with area rather than volume was one of the clues that led to the holographic principle. The idea that the information content of a region of space is encoded on its boundary rather than its interior. The fuzzball picture gives this a concrete physical meaning. The entropy of the fuzzball is carried by the strings and branes at its surface, whose number of configurations scales precisely with the horizon area. The fuzzball proposal is not without its difficulties. For the astrophysical black holes we observe, formed from stellar collapse with no special symmetry or charge, a complete fuzzball description has not yet been worked out. The calculations that produced exact entropy matching were performed for simplified, idealized cases that are easier to handle mathematically. Whether the same picture applies to realistic black holes is an open question. Some physicists have argued that the differences between idealized and realistic black holes are unlikely to change the qualitative conclusions. Others have been more cautious, noting that the extension from the idealized to the realistic case involves assumptions that have not been fully justified. There is also the question of what a fuzzball looks like from the outside during the process of formation. When a massive star collapses, the standard picture has it crossing its own Schwarzschild radius and disappearing behind an event horizon in a finite time, as measured by a distant observer. Though the collapse appears to slow and freeze from that observer's perspective, due to gravitational time dilation. In the fuzzball picture, the formation process must somehow produce a physical surface at the scale of the horizon, rather than an empty geometric boundary. How this transition occurs dynamically, what happens during the collapse itself, is an area of active investigation. What the fuzzball offers, despite these open questions, is something that very few alternatives to the black hole can claim. It is embedded in a broader theoretical framework with a large body of internal consistency checks. It resolves both major problems of the classical black hole model, the singularity and the information paradox, through the same mechanism. And it has produced at least one prediction, the entropy matching, that agrees precisely with an independently derived result. Whether string theory ultimately proves to be the correct description of nature is a separate question. But within that framework, the fuzzball is a serious, detailed, and mathematically grounded alternative to the black hole that deserves to be taken seriously on its own terms. Chapter 8: Dark Energy Stars and Other Models. The Gravastar and the fuzzball are the two most developed alternatives to the classical black hole, but they are not the only ones. A broader family of theoretical proposals has emerged over the past several decades, each approaching the singularity and information problems from a different angle. They vary considerably in their assumptions and their mathematical foundations, but they share a common motivation: the conviction that the interior of a black hole cannot be what the classical model says it is. One of the earliest and most straightforward alternatives is the dark energy star, proposed by George Chaplin in 2005. Chaplin's argument drew on an analogy with condensed matter physics, the study of how matter behaves in bulk at the scales of everyday materials. He suggested that the event horizon of a black hole might function like a quantum phase boundary, a surface at which the properties of space-time change abruptly, in the same way that the properties of a material change at the boundary between two phases. Inside that boundary, in Chaplin's model, the collapsing matter converts into dark energy, the same form of energy thought to be driving the accelerating expansion of the universe. The interior is held open by the repulsive pressure of that dark energy, preventing the formation of a singularity. The external geometry remains identical to that of a black hole. The dark energy star shares several features with the Gravastar. Both replace the singular interior with a dark energy-dominated region. Both preserve the external gravitational signature of a black hole, while modifying its internal structure. The differences are primarily in the details of the phase transition mechanism and the properties of the boundary layer. Chaplin argued that his model made a specific observational prediction, that the gamma-ray bursts associated with certain energetic astrophysical events might carry signatures of the phase transition at the horizon surface. This prediction has not been confirmed, but it has not been definitively ruled out either. Another proposal is the Planck star, developed within the loop quantum gravity framework by Carlo Rovelli and Francesca Vidotto in 2014. The Planck star takes the loop quantum gravity resolution of the singularity, the bounce that replaces infinite collapse with a minimum volume, and asks what it implies for the life cycle of the object from the outside. Their answer was that a collapsing star reaches Planck density, bounces, and then re-expands. From the outside, this process appears enormously slowed by gravitational time dilation. What takes a fraction of a second in the interior might correspond to an astronomically long time as seen from a distant observer. But eventually, the re-expanding interior would cause the apparent horizon to shrink and disappear, releasing the information that had been trapped inside. The Planck star is not stable indefinitely. It is a temporary state, a very long-lived but ultimately transient phase in the life cycle of a collapsed object. Regular black holes represent a somewhat different approach. Rather than replacing the black hole with an entirely different kind of object, regular black hole models modify the interior geometry of general relativity to remove the singularity while preserving the event horizon. The first and most studied example is the Bardeen black hole, proposed by James Bardeen in 1968, making it one of the earliest alternatives in the literature. The Bardeen solution replaces the singular center with a regular, non-singular core. The geometry transitions smoothly from the strongly curved region near the center to the flat space-time of the exterior without passing through a point of infinite curvature. Later work by Irina Dimnikova and others produced additional regular black hole solutions with similar properties. Regular black holes are mathematically cleaner than some of the more exotic alternatives. They do not require string theory, dark energy interiors, or phase transitions. They simply modify the metric, the mathematical object that describes the geometry of space-time, in a way that eliminates the singularity while leaving the exterior geometry intact. The cost is that the modification requires some form of matter or energy with unusual properties at the center, typically something with a repulsive pressure strong enough to halt the collapse. What that matter or energy actually is, physically, is a question that regular black hole models do not always answer in detail. What this broader landscape of alternatives reveals is something worth holding quietly for a moment. The black hole is often presented as a single, well-defined object, something we have discovered, measured, and understood. But what the theoretical literature shows is that the name covers a wide range of possibilities. The external appearance is constrained by observation. The interior is not. An enormous variety of internal structures are consistent with everything we can currently measure from the outside. The question of what these objects actually are in their deepest interior remains genuinely open, not because the observations are poor, but because the observations, by their nature, cannot reach inside. Each of the alternatives described in this chapter and the last represents a different answer to the same question. They cannot all be correct. Some may be ruled out by future observations. Some may turn out to require assumptions that do not hold. But the existence of so many serious, mathematically grounded proposals is itself informative. It tells us that the classical black hole model, for all its successes, has not closed the question of what these objects are. It has only opened it more carefully. Chapter 9. The Event Horizon, Real or Apparent. Of all the features associated with black holes, the event horizon is the one that carries the most weight. It is the boundary that defines the object. It is the line beyond which nothing returns. It is what makes a black hole rather than simply a very dense, very massive star. And yet, the event horizon, examined carefully, turns out to be a more subtle and contested concept than its familiar treatment suggests. There are, in the technical literature, two distinct kinds of horizon associated with black holes. The first is the absolute event horizon, the one that appears in the classical general relativistic description. The absolute horizon is defined globally, in terms of the entire future history of the spacetime. A point in spacetime is inside the absolute event horizon if light emitted from that point can never reach a distant observer, no matter how long the observer waits. This is a clean and precise definition, but it has an unusual property. Whether a given point in spacetime is inside the absolute horizon depends on what happens in the future, on whether the black hole ever evaporates, and on the entire subsequent history of the universe. The absolute horizon is, in a meaningful sense, defined by information that no local observer can access. The second kind is the apparent horizon. The apparent horizon is defined locally. It is the boundary of the region from which light cannot currently escape, given the present geometry of spacetime. Unlike the absolute horizon, the apparent horizon can be identified without knowing the future. It is the outermost surface at which outgoing light rays are not moving outward, but are instead being held in place by the curvature of spacetime, what physicists call a trapped surface. In a classical, non-evaporating black hole, the absolute and apparent horizons coincide, but in a black hole that is losing mass through Hawking radiation, they can differ, and that difference turns out to matter considerably. Stephen Hawking, in a paper published in 2014, made a statement that attracted significant attention. He argued that absolute event horizons, in the strict sense, do not exist. His reasoning was connected to the firewall argument. The firewall paradox had shown that the combination of information preservation and smooth horizon crossing was inconsistent within the framework of quantum mechanics. Hawking's response was to suggest that the absolute horizon, the eternal, globally defined boundary, should be replaced by an apparent horizon, which is temporary and can eventually release information as the geometry of spacetime evolves. He was careful to note that this was not a claim that black holes do not exist in any sense. It was a claim that the specific mathematical object called the absolute event horizon may not be the right description of what these objects actually have. The distinction matters because of what it implies for the interior. An absolute event horizon is permanent by definition. Once formed, it persists until the black hole evaporates entirely, and the evaporation itself, in the strict classical picture, takes an extraordinarily long time. An apparent horizon is more flexible. It is defined by the local geometry, and as that geometry evolves, as the black hole loses mass, as the surrounding spacetime changes, the apparent horizon can shift, shrink, and eventually disappear. Information that is trapped behind an apparent horizon is not trapped permanently. It is trapped for a very long time, but the horizon that traps it is not an absolute boundary. It is a feature of the current geometry that will eventually dissolve. This distinction has practical consequences for the alternatives we have been discussing. Many of the alternative models, Gravastars, Fuzzballs, Planck stars, do not have absolute event horizons. They have surfaces or boundaries that function like horizons in the sense of being extremely difficult to escape from, but that are not eternally trapping in the way the absolute horizon is. In some models, the apparent horizon forms during collapse and then gradually retreats as the object evolves, eventually releasing whatever fell in. The object looks like a black hole for an astronomically long period, but it is not, in the strict technical sense, a black hole, because it does not have an absolute event horizon. Whether this distinction is physically meaningful or merely semantic depends on the timescales involved. If the apparent horizon retreats and releases information only after a time much longer than the current age of the universe, then for all practical purposes, the object behaves as a black hole. The difference would be undetectable by any observation we can currently conceive of. But for the theoretical questions, for the information paradox, for the singularity problem, for the question of what these objects fundamentally are, the distinction is significant. What this chapter points toward is a possibility that is easy to overlook in discussions of black holes. The event horizon is not a physical surface in the way that the surface of a star is a physical surface. It is a geometric feature, a property of the spacetime around a massive object. Whether that geometric feature takes the absolute or apparent form, whether it is permanent or temporary, whether it is precisely where general relativity places it or subtly modified by quantum effects, these are open questions, and they are connected in ways that theorists are still working out to the question of what exists at the center of these objects and how the information they contain is ultimately accounted for. Chapter 10. What quantum gravity might reveal. Every problem we have examined in this video, the singularity, the information paradox, the nature of the event horizon, traces back to the same underlying gap. General relativity and quantum mechanics are both extraordinarily successful theories, each within its own domain, but they have never been fully unified. A complete theory of quantum gravity, one that describes how space-time behaves at the smallest scales, where both gravitational and quantum effects are simultaneously important, does not yet exist. And yet, it is precisely such a theory that would be needed to answer the deepest questions about black holes. This is not a comfortable position for physics to be in. The two greatest theoretical achievements of the 20th century are mutually incompatible at the scales where black holes push them into contact. General relativity treats spacetime as a smooth, continuous fabric that bends and curves in response to mass and energy. Quantum mechanics treats physical systems as fundamentally probabilistic, described by wave functions that evolve according to precise rules. Combining them requires not just a technical extension of one or both theories, but a rethinking of what spacetime, matter, and information actually are at the most fundamental level. Several serious research programs have taken up this challenge. They differ in their assumptions, their mathematical tools, and their current state of development. But each of them has something to say about black holes, and what they say is consistent, in broad terms, with the conclusion that the classical black hole interior is not the final answer. Loop quantum gravity is one of the most developed approaches. It begins with the assumption that spacetime itself is quantized, that at the Planck scale, space is not a smooth continuum, but is composed of discrete units connected to each other in a network described by what are called spin networks. The geometry of spacetime in this picture is not a background that physical processes occur against. It is itself a physical system with quantum states and quantum fluctuations. At the Planck density, the discrete structure of spacetime generates a repulsive pressure, the same mechanism that produces the bounce in the Planck star model, that prevents the formation of singularities. Quantum geometry in loop quantum gravity is self-regulating in a way that classical geometry is not. Loop quantum gravity has been applied to cosmology as well as to black holes. In the cosmological context, it predicts that the Big Bang singularity is replaced by a big bounce, a moment of minimum but finite volume from which the current expansion of the universe emerged. The parallel with the black hole interior is direct. In both cases, a singularity predicted by classical general relativity is replaced, in the quantum gravitational treatment, by a finite and physically meaningful event. The universe did not begin at a point of infinite density. A black hole does not end at one either. String theory approaches quantum gravity from a different starting point. Rather than quantizing spacetime geometry directly, it proposes that all particles and forces, including gravity, arise from the vibrations of fundamental strings. In this framework, The geometry of space-time is not fundamental but emergent. It arises from the collective behavior of strings in a way that resembles smooth space-time, only at scales much larger than the string length. At the string scale, the notion of a point in space loses meaning, and with it, the possibility of a point singularity. The most significant contribution of string theory to the black hole problem is the ADS/CFT correspondence, already mentioned in the context of the information paradox. This correspondence between a gravitational theory in a space with a particular geometry and a quantum field theory on its boundary provides a precise mathematical framework in which questions about black holes can be translated into questions about ordinary quantum systems. In the boundary theory, information is manifestly preserved. The correspondence therefore strongly implies that information is preserved in the gravitational theory as well, including during black hole evaporation. It does not specify the mechanism by which information escapes. That remains an active area of research, but it establishes the conclusion with a degree of mathematical rigor that purely heuristic arguments cannot match. A more recent development emerging from the intersection of quantum information theory and quantum gravity concerns what is called the island formula. In 2019, a group of researchers found a way to calculate the entropy of Hawking radiation that incorporated contributions from regions inside the black hole, regions called islands, through a quantum gravitational effect. The result was that the entropy of the radiation follows a curve consistent with information preservation, rather than growing without bound as Hawking's original calculation implied. The island formula does not require a complete theory of quantum gravity to apply. It uses semi-classical methods, quantum field theory in a curved space-time background, combined with a specific prescription for how to include gravitational contributions to entropy. Its derivation is technically involved, but its conclusion is clear. Information is not lost. It escapes in the Hawking radiation, encoded in correlations that a purely classical treatment of the horizon misses. What quantum gravity approaches collectively suggest is that the black hole interior is not a fixed classical geometry. It is a quantum system, complex, dynamic, and subject to the same principles of information conservation that govern every other quantum system in the universe. The singularity is not a destination, but a symptom. The event horizon is not an absolute barrier, but a feature of an approximate description that breaks down at the scales where quantum gravity becomes important. The complete theory that would make all of this precise does not yet exist, but the direction it points is reasonably clear. Whatever black holes turn out to be at the deepest level, they are almost certainly not what the classical model describes at their center. Something else is there. Something that a future generation of physicists, armed with tools we do not yet have, may eventually be able to describe with the same clarity that general relativity brought to the outer geometry of these remarkable objects. Chapter 11. What the James Webb Space Telescope is finding. The theoretical questions we have been exploring do not exist in isolation from observation. Physics moves forward through the interplay between what the mathematics predicts and what the instruments find. And in the past few years, one instrument in particular has been returning data that complicates the standard picture of black holes in ways that theorists are still working to understand. The James Webb Space Telescope, launched in December of 2021, was designed to observe the universe at infrared wavelengths with a sensitivity and resolution far beyond any previous facility. Its primary scientific goals included the study of the earliest galaxies, objects so distant that their light has been traveling toward us for more than 13 billion years, reaching us from a time when the universe was only a few 100 million years old. What Webb has found in that early universe has surprised a significant number of astronomers. The surprise is not that early galaxies exist. It is how massive they are, and how massive the black holes at their centers appear to be. The standard model of cosmic structure formation predicts that galaxies and their central black holes grow together over time, through a combination of mergers and the gradual accumulation of gas and stars. Supermassive black holes in this picture begin small and grow slowly, constrained by the rate at which they can accrete surrounding matter, a rate that is itself limited by the radiation pressure that hot infalling gas generates. There is a theoretical maximum rate at which a black hole can grow, known as the Eddington limit, and sustained growth above that rate is considered physically difficult to maintain. Webb has identified galaxies in the early universe hosting black holes that appear to be far more massive than the standard formation model comfortably accounts for. Some of these objects, observed at redshifts corresponding to times when the universe was less than 1 billion years old, contain black holes with masses of hundreds of millions or even billions of solar masses. Growing a black hole to that size in the time available, starting from the stellar mass seeds that standard models predict, requires either sustained accretion at or above the Eddington limit for an implausibly long period, or a formation mechanism that produces much more massive seeds than the standard picture allows. Several explanations have been proposed. One involves the direct collapse of massive clouds of primordial gas in the early universe, bypassing the stellar stage entirely and forming black holes of tens of thousands of solar masses directly from the gas cloud. These direct collapse black holes would provide a much more massive starting point for subsequent growth, making the masses Webb observes easier to reach within the available time. Another proposal involves the dense stellar clusters that formed in the early universe, where stellar collisions and mergers could produce unusually massive stars that then collapsed into black holes significantly heavier than those produced by ordinary stellar evolution. A third possibility, more radical in its implications, is that some of the objects Webb is observing are not black holes formed from collapsed matter at all, but primordial black holes, objects that formed in the very early universe from density fluctuations in the primordial plasma before any stars existed. Primordial black holes have been proposed as candidates for dark matter, and while current constraints rule out primordial black holes as the dominant component of dark matter across most mass ranges, a population of massive primordial black holes in the early universe could in principle provide the seeds for the supermassive objects Webb is now finding. What makes the Webb observations particularly significant for the questions this video has been exploring is what they imply about the relationship between black hole mass and galaxy mass in the early universe. In the local universe, the relatively nearby galaxies we can study in detail, there is a well-established correlation between the mass of a galaxy's central black hole and the mass of the galaxy's stellar bulge. This correlation suggests that galaxies and their black holes grow together, regulating each other's growth through feedback processes. Webb is finding early universe objects where this correlation appears to break down, where the black hole is disproportionately massive relative to its host galaxy, suggesting that the black hole grew first and the galaxy caught up later, or that the growth processes in the early universe operated differently from those we observe nearby. None of this directly confirms or refutes any of the alternative models discussed earlier in this video. Webb is observing these objects from the outside, through their light and their gravitational influence on surrounding matter. The same external signatures that cannot distinguish a classical black hole from a gravastar or a fuzzball. But the unexpected masses and the apparent breakdown of the local scaling relations suggest that our models of how these objects form and grow are incomplete. And models that are incomplete in their description of formation and growth may also be incomplete in their description of internal structure. What Webb is doing, in the broadest sense, is expanding the range of phenomena that any successful theory of black holes must account for. The classical model was built primarily on observations of black holes in the local, relatively mature universe. The early universe objects that Webb is revealing are more extreme, more puzzling, and less well explained by the standard picture. They are not anomalies to be set aside. They are data, careful, precise, and accumulating, that the next generation of black hole theory will need to incorporate. Chapter 12. Living with Uncertainty. There is a particular kind of discomfort that arises when a well-established scientific model turns out to be incomplete. It is different from the discomfort of not knowing something entirely. When we do not know something, the path forward is simply to look more carefully. But when a model that has worked extraordinarily well for decades begins to show its edges, when the equations that have passed every observational test begin to predict things that cannot be physically real, the situation is more subtle. The model has not failed. It has revealed the boundary of its own validity, and that boundary is itself a discovery. This is where black hole physics currently stands. General relativity has not failed. Its predictions for the external geometry of black holes have been confirmed with remarkable precision. The Event Horizon Telescope images, the gravitational wave detections, the stellar orbits around Sagittarius A star, all of these are consistent with the theory to a degree that would have seemed extraordinary to the physicists who first worked out the mathematics a century ago. And yet the same theory, applied without modification to the interior of a black hole, predicts a singularity that almost no one believes is physically real. It predicts an information loss that almost no one believes actually occurs. It predicts an event horizon whose precise nature becomes deeply problematic when quantum mechanics is taken seriously. The response to this situation within the physics community has not been panic or crisis. It has been something quieter and more productive, a sustained, careful, and genuinely open investigation into what lies beyond the current model. The alternatives we have examined in this video, Gravastars, Fuzzballs, dark energy stars, Planck stars, regular black holes, are not fringe proposals advanced by physicists dissatisfied with the mainstream. They are serious theoretical contributions published in peer-reviewed journals developed by researchers who understand general relativity and quantum mechanics deeply and are trying to reconcile them honestly. What these alternatives share is not a single answer, but a common question. They all ask, what is actually happening at the scales and conditions where the classical model breaks down? They all take seriously the possibility that the interior of what we call a black hole is not what the textbooks describe. And they all proceed from the recognition that our observational access to that interior is, by the nature of the object, severely limited. We cannot look inside. We can only infer from the outside and hope that the inferences eventually converge on something we can test. That limitation is worth sitting with. It is not a temporary technological constraint that better telescopes will overcome. It is, in the classical picture, a fundamental feature of the object. The event horizon, if it exists as general relativity describes, is a one-way boundary. No signal from inside it can reach us. No observation we can make from the outside can directly reveal what is happening within. We are, in a precise and unavoidable sense, permanently excluded from the interior of these objects, if the classical model is correct. But the classical model may not be correct, and this is where the situation becomes genuinely interesting, rather than simply frustrating. If the alternatives are right, if what we call black holes are actually gravastars or fuzzballs, or objects with apparent rather than absolute horizons, then the exclusion may not be permanent. An apparent horizon can retreat. A physical surface can emit radiation that carries information. A quantum gravitational interior can, in principle, leave observable signatures in the Hawking radiation or the gravitational wave ring down. The universe may not be keeping these secrets forever. It may simply be keeping them for a very long time. Science is unusually comfortable with very long time scales. It is also unusually comfortable with open questions, more comfortable, perhaps, than any other human endeavor. The history of physics is full of periods during which fundamental questions remained unresolved for decades or even centuries before the right framework arrived to answer them. The nature of light, the structure of matter, the origin of the elements. All of these were genuinely open questions for long stretches of time, and all of them eventually found answers that were more surprising and more beautiful than the questions had suggested. The black hole question is in that tradition. It is not a failure of understanding. It is an invitation, extended by the universe itself, written in the language of mathematics and light and gravitational waves, to think more carefully about what space, time, matter, and information actually are. The objects at the centers of galaxies, the remnants of collapsed stars, the sources of gravitational waves that travel 1 billion light years to move our detectors by less than the width of a proton. These are not just extreme versions of familiar things. They are the places where the familiar runs out, and where something new is waiting to be understood. For now, they remain what they have always been: quiet, distant, and vast, bending light around themselves with a patience that has nothing to do with urgency. Whatever they are on the inside, whatever physics eventually reveals about the nature of their interiors, they will continue to sit at the centers of galaxies, pulling matter slowly inward, long after every question we have asked about them tonight has found its answer. If this was a good companion tonight, a like or a subscribe helps other curious minds find their way here.